How much of resistant motion have you guys done in physics?
None. Friction.
Friction. Okay. Talk to me about friction.
That was like year 11 and
Oh, I remember doing
we
that.
just calculated frictional force.
Yeah. Okay. So you know, like in physics, I think the focus is on kind of the description, a lot of description on these. There are calculations, but you know, like when you talk about friction in physics, in year 11 physics, you look at like different types of friction, like static friction or rolling friction, all these like intricacies, right? Whereas in mathematics, we tend to focus more on the calculations themselves. I think it's definitely helpful to have a good understanding of, you know, what friction is and the resisted motion there. But what I'm going to show you is a large part very calculation heavy. Okay, so utilizing the skills that you've been doing, integration, rearranging, solving, writing your acceleration and velocity in terms of different variables, in terms of displacement, in terms of time, that's going to be a big focus on this here. So yeah, so resistance, how would you describe resistance though? Let's just get some understanding here.
It's like a force that slows.
Yeah, force acting in the opposite direction.
Yeah. On motion.
Yeah, that's good.
How easy is it?
Okay, that's the first thing. And retardation is what I've looked up, apparently, is the acceleration acting in the opposite direction to the motion. So what the object itself experiences.
Is that like a... Wait, does that shade near that?
There's a definition there, so I thought I might include it.
Simple harmonic motion. Are we going to do vertical resistance?
We will. Well, how'd you know?
And then both of them.
That's called projectile motion.
Again, Matt, how easy is this one?
So the object experiences this, right? So what I kind of want to talk about is when we talk about a force, right? What is Newton's formula that we're used to seeing when you think about forces? Was that Newton's formula, or is it one of Newton's laws?
Force. Oh.
Is that Newton's law? Actually, yeah.
F equals ma.
Yeah, F equals to ma, right? So what we're going to be looking at is we are going to be looking at the forces that involve acceleration. Acceleration is interesting because we've looked at a few different ways to write acceleration, right? We know that acceleration, x double dot, is equal to not only you know, the second derivative of your displacement. How else can we write it? We could write it as d dx half v squared dv dt. Yeah. Now, this d dx half v squared thing, I just want to make an emphasis on how you actually come up with something like this, right? If you think about dv dt and you think about your chain rule, okay, so dv dt can be written another way. This is also in your formula sheet, by the way. dv dt, if you think about your chain rule, right, can be written in a way like this. Would you agree? Because all you're saying is that these dx's will cancel out and you get left with dv dt, right? But actually, what's this guy over here? dx dt. That's velocity, right? So another way to write this is v dv dx. And that's going to be useful later on. In Cambridge, they tend to write this as v times v dash, but I think that's a bit unhelpful because then you don't know what it's derived with respect to. So this is another form that's going to come in handy a little bit later on, okay? So far, the idea is we'll be utilizing F equals to ma, depending on what mass and what forces, what acceleration we're given, and also these various forms of acceleration here, and we'll be applying these to our problems, okay? So that's the first thing we need to note down. Now, I've got a little flow chart here I'll share with you guys in a moment, but basically it tells you which one of these forms you may need to rely on depending on the situation, right?